Another section, we're going to talk detail about the microbial growth and the nutrition. I just want to make sure that this is recorded. Okay. Okay. Lecture 4, we will talk about is microbial growth and the nutrition requirements related to the different of the bacterial media, and we also going to practice in the lab. So here we are talking about is the characteristics, bacterial growth, the external factors impact bacterial growth, and then we're going to do the enumeration, and also a little bit identification. And the tricky stuff here is we're going to talk about the detail of the bacterial media. That makes it a little bit tricky. Okay, so let's go these one by one. First thing first, how bacteria grow. We gave them a terminology called binary fission. Bacteria in a very optimal status, optimal conditions, there always is 1 become 2, 2 become 4. So what happens if you see, there is a bacteria, the DNA attached to the cytoplasmic membrane. Then the DNA will do the replication. Sometimes they're going to be doing it independently. Sometimes they're using the material inside of these the cell wall, cell membrane system. It depends. Then the cell wall will be formed, and then they separate. And each of the copy of the DNA will be exactly transferred from the mother cell to the daughter cell, and this wall will later on be separate and become a daughter cell. And this cross wall, we call it a speculum. So, by this situation, we always know a bacteria is 1 become 2, 2 become 4, 4 become 8, 8 becomes 16, 16 becomes 32. So you need to know a little bit of math. This is 2 times 0, 2, 1, 2, 2, 2, 3, and 2, 4, and 2, 5. We will use this one later on, okay? Second, the generation time. What is the generation time? Which means the time required for a population to double in the number. Some of the bacteria are very short. We mentioned about the E. coli. That's why E. coli is always a good culture in the lab because it grows really quick. The doubling time is every 18 to 20 minutes. That means if I grow a bacteria, only 1 cell in the morning, then later noon, it's going to become 10 to the 6 cells, 10 to the 8 cells, a tremendous amount of going to generate. However, some of the bacteria, the doubling time is very short. Let's say Mycobacterial tuberculosis. That required doubling time is 12 to 24 hours, which means 1 cell becomes 2 cells almost a day. That is the reason we need acid-fast stain. Because the acid-fast stain, we will know the sputum sample has Mycobacterial tuberculosis, or we say it's highly possible has Mycobacterial tuberculosis. Then we have to do the treatment. The reason is that we can't get isolation to wait to confirm Mycobacterial tuberculosis. This has to do in the reference lab, usually take about a week to 10 days. At this moment, the patient maybe already cannot survive. That's why we have to use acid-fast stain. Okay? So just let you know the generation time, some bacteria are very quick, some bacteria are very slow. This comes out with some of the mass. Okay, this is talking about the growth rate and the generation time. So we say at the time 0, a bacteria number is N0. And then let's say at time t, a bacteria number is NT. And we want to talk about is how many generations at time t, or we say after t times. Okay, we can say that. what it is going to be looks like. So what's the formula for that? This NT equals N0 multiplied by 2N. In the bacteria calculations of population, we were using log because it's too large. So we usually don't talk about the 1 cell or 2 cell. It's only in the exception is some of the regulation for the bacterial pathogen is zero tolerance. For example, in the ground beef, the E. coli 0157H7 is zero tolerance. You're not allowed to have 1 cell. At this moment, we say it's cell. 1 cell, 2 cell, 3 cell. Here, we talk about a large population. Because after your generation, you will become 2, 2 become 4, 4 becomes 8. Tremendous amount of going to generate. Therefore, we have to transfer them to log. If we do log transfer, this is a log 10 most of the time, okay? If it's a log 10, we don't write 10 anymore. What is going to become? Log 10 and 0 multiplied by 2n. Then becomes log n0 add log 2n. Then becomes what? Log n0 add n log 2. Okay, what are we going to calculate? We want to calculate this n, is that right? So if you do a transfer, it's log nt is minus log n0 and then divided by log 2. What is log 2? How to do this? This is kind of like equals 2, is that right? What is this? 0.300 or 301. Okay, so this one you could simply to say is log nt minus log n0 will become 0.301. And this is the number of the generation. And the number of the generation, if we talk about a specific time, let's say a t, divided by t, it comes with a k. This k is growth rate. Now then, how are we going to do the doubling time? Doubling time, this guy becomes 2n0. Is that right? So, how are we going to do the doubling time? Let's say this k. This case becomes log 2n0 by log n, then divided by 0.30 at the g there. So what are going to be there? Log 2 add log n0 minus log n0 divided by 0. Divided by g. This is gone. This is equals z. This is gone. So that comes what it is. The generation time is the reciprocal of the growth rate constant. G equals 1 divided by k. Okay, you can read it through here. This is just an introduction. I don't test your maths because I don't think your maths are very, very good. So we don't test your maths. So I offer the time, let's do some of the tricky stuff. Do you know all this quiz? Did you take AMC 8, the math competition in your high school? How to do that in 2 seconds? This is non-limited, is that right? Then go here is 2. So what is x? Sorry, the x is 2. What is that? Is that right? We can do this in a couple of seconds if it's a very smart kids. Is that right? So the level is different. That's why I want to just show you these math calculation, but we don't require you in the lab because it's not a math class. But I want to let you know we can do the calculation. Now most of the time right now, they can do this software. There's a software to do the calculation. Then is come out another big discipline of the microbiology called predictive microbiology modeling science. We can talk about that the whole semester. There's different modeling when you talk about thermal inactivation and in a different products because the metrics of the products, the thickness, the flow rate, the morphology will changing those the bacteria grow and also the bacterial decontamination. So I just want to let you know there's a big mass behind it. most of the time we can do a software, use a software to solve. Okay, here just some of the example from our slides, how the story behind it. But the key thing is the next slides. We really want to mention is the bacteria growth curve. This is the key for this section. And for the exam, I hope everybody can draw a bacterial growth curve. This is important. So first of all, you need to know, bacterial growth is not linear. It's not one cell suddenly become 1 million cells. Not like this. Bacterial growth has steps, has a different stage. So when you draw a picture, we have x-axis and the y-axis. The x-axis is always time, using second. Let's say E. coli. Okay, microbacteria, maybe we use day or hour. What is the y-axis? This is usually the population. And we were using log 10 colony forming unit per ml. We'll talk about this later on in the lab. Or you can say just the cell culture population, which is like cells per ml. And the bacterial cell growth have a 4 different stages. The curve basically looks like this. At the beginning, there is a preparation stage we call lag phase. Every time the bacteria moving into a new environment, they have get accustomed to the new environment. Their DNA, their RNA, their nutrition level all have to adjust it. So there is a time to prepare. We call it a lag time or buffering time. So we call it a lag phase. After they are accustomed to the environment, they're going to grow dramatically. They're going to grow is in a log base. So the second stage, we call it a log phase. So the bacteria keep growing, keep growing. At the same time, they're going to generate waste. Is that right? This is like you have to go restroom. It's the same thing. In their small environments, they're taking nutrition, they come out of the waste. The waste is a toxication for them. Nobody going to clean the restroom for them. Is that right? They're all there. So the toxication material going to start to killing them. So they're going to reach a stage. Their growing number and the dead number is balanced. So that's why we call it a stationary phase. At this moment, the growing and death number are balanced. Later on, they're going to start to die. So we call it a death phase. Because the toxication material going to generate there from their waste, the number will dramatically grow. So I want to tell you one thing. If it's an E. coli cell, after growth 35 degrees Celsius in 24 hours, they will reach 10 to the 8th cells per ml. If this tube you're going to keep there in the room temperature, they started to die, start to die. About a week or 2, they started to die. You put them in the refrigerator, it's going to, about a month, they will die. At low temperature, they can survive a little bit. Eventually, they will be died. Now, what's the way to preserve them? You need to add glycerol. We use a semi-solid media to add glycerol, they can survive. Because glycerol will protect them. That's not the best way. How about if the bacterial culture I need to preserve for a long time? What are you going to do? Put in minus 20 degrees Celsius freezer. Or put at minus 80 degrees Celsius freezer. Then you got to frozen. Because when they frozen, their enzyme is deactivated. So they're not going to grow. But I want to protect something. Because deep freezing, what happened? The tissue for them, they don't have a tissue, but the structure for them will be cracking. We have to protect it, is that right? So you need to add some of the crop protectants, like sugar. and sometimes glycerol is an example. So the best way to do is in a semi-solid glycerol media, you put the bacteria, let it grow, then deep freezing at minus 80 degrees Celsius. The bacteria can stay there for about 3 years probably. So just to let you know, the bacteria culture we in the lab, it will be died after a certain time because the growth curve is like that. Okay, so this is important. Next, we can grow bacteria, but does not mean every bacteria we can really culture. Some of the bacteria, they have viable capability, will cause problem, but they are not culturable. We talk about them viable but non-culturable. How are we going to do that? The traditional methods use agar media, they're not going to cultivation. We have to rely on molecular methods like real-time PCR to test the genome. We test the genome, we know the presence of the bacteria. This is the same thing like you do the COVID-19 test. You're using PCR testing. We see the genome there, the virus is there. But obviously there is a difference. So that's why it's usually 95% correct. Is that right? So this is something we want to talk viable but non-culturable. Then, bacteria in all kinds of the environment, they eventually will be died. We call that suicide, but quotation mark suicide. It's called a programmed cell death. Like our animal cell and human cell, there's a programming to let them die gradually. But if like in a human being, if your programmed cell death have the trouble, they have the mutation of the gene, what you're going to end up is a cancer, is that right? For bacteria, they just directly die. So same as a human being, they have a programmed cell death. Next, we want to talk about factors affect microorganism growth. We want to very quick talk about the first two. We want to spend in time talk about the water activity. Then oxygen concentration we'll talk about next week. First of all, everybody knows pH, so I'm not going to emphasize this too much. Equals minus log the concentration of protons, or we say hydrogen ions. This range from 0 to 14. Do you know what is 0? Did you ever, they tell you the battery, don't throw them away. You have to preserve the put in a recycle bin or somebody take it. Battery acid is 0. Very highly corrosive. What is 14? 10 mole sodium hydroxide. And we like the ones in the middle, is that right? pH 7, neutralized. Okay, so this is pH. Same as a human being. The bacteria, optimal growth, majority of them is around the pH 7. I will say around the pH 7. Sometimes 6.5 to 7.5. The reason is, same as a human being, at the pH 7, their enzyme is in a very optimal function. That's why neutrality pH is the optimal pH for the bacterial growth. If the pH is less than 4.0, lots of the bacteria will not grow. However, yeast and the molds will still grow. They are a little bit resistant to the low pH. Based on the pH value, we can classification bacteria into, microorganisms into acidophiles. Their optimal pH is 0 to 5.5, like a fungi. Most of the bacteria we are talking about is neutrophil. Most of the bacteria is neutrophil. Because their pH range is 5.5 to 8.0. That's a neutrophil. Some of the bacteria, like Micrococcus, Pseudomonas, Bacillus, they are alkaline phials. Their pH range 8 to 11.5, a little bit alkaline. So here is the thing, pH is important to control the bacteria. Bacteria has to really maintain the pH value and really has to be adjust their external environments or internal environments to combat if there's a high pH. Most of the time they exchange with potential for the protons to maintain the pH. There is a bigger problem in the food industry will come out, is we call acid-resistant bacteria. This is happening in the beef industry a lot. The beef industry, you have to set up a HACCP plan, which is Hazard Analysis Critical Control Points Plan. Based on the new regulation of the FSMA, you heard about that, maybe it's the Food Safety Modernization Act for the process preventive control. You may have to use some antimicrobials. Lots of the time we are using lactic acid. Okay, we are using acetic acid. These are acid, is that right? So, you're gonna keep spraying. When you keep spraying, some bacteria are gonna die, but there are some bacteria gonna survive. How the bacteria survive? They can pumping out their pH, their protons, and then to keep their microenvironments stable, so they exchange with potassium. Like we said in the slides, there are more and more bacteria accustomed to the environment, they'll become acid resistant. What's a bad thing for these acid resistant bacteria? Is you are spraying with new antimicrobials, it's not gonna work. And even this beef chunk, you go ahead to cook it, these bacteria may be difficult to kill because they'll generate the cross protection, throwing the forming of the resistant mechanism. That gives you a big trouble with the meat industry. So what do you have to do? These sanitizing, these antimicrobials, you have to do the rotation. You can't keep using the same one. If you have an acid-based sanitizing, you may have to prepare the alkaline-based one to do the rotation, that they will not become acid-resistant too fast. Okay, so this is something I would love to mention. Temperature. Now, obviously, temperature is related to the enzyme. So, for every bacteria, there is an optimal temperature right in the middle, there's a minimal and a maximal temperature. Usually, it's a lower and upper level limit. Based on the temperature requirements, we could separate a bacteria into 5 different categories. First of all, majority of the bacteria we are talking about in the lab is mesophiles. Their optimal temperature range is 20 to 45 degrees Celsius, like E. coli, like Salmonella. However, there is some of the bacteria can survive in a refrigerated temperature. Let's say Listeria monocytogenes. This is a guy will cause a major trouble for lots of the ready-to-eat meat, like ham, like turkey breast. The reason is, this is a bacteria can grow very well in the refrigerated temperature. So we call it cycrotrophs. This is called cycrotrophs. Cycrotrophs. Same as Pseudomonas, as a spoiled bacteria. They grow very well in the refrigerator. So that's why the refrigeration to preserve the bacteria only a short time. Long time it's going to grow because lots of the bacteria can grow. Some of the bacteria can even grow in a very low temperature. It's like a chilling and freezing temperatures. That's called cycrophiles. What's the difference between that? This is the name is PHILE. This is TROP. When you have a cycrophiles, the low temperature, their optimal temperature is much lower. Those type of the bacteria is usually in a deep ocean marine, like Antarctic, Arctic area. Those in the very deep level of the ocean, the bacteria survive. So it's an environmental bacteria. Some of the bacteria resistant to the heat. We call it a thermophiles. Let's say Bacillus. The Bacillus is resistant to the heat, so it's a thermophile. There's a lots of the bacteria. If you go Yellowstone National Park in the hot spring, you will find some of the bacteria still survive there. Those are hyperthermophiles. There is one bacteria culture we used in the lab for testing the function of the autoclave. It's called Geobacillus. This is a very good example. Talk about the hyperthermophiles. They can survive in the temperature even 110 degrees Celsius. So if your autoclave has to work in, you have to reach much higher than this temperature to kill geobacillus. If the geobacillus is survived there, which means your autoclave is failed the inspection and the validation. This tells you a temperature range for microbial growth. So we have cycrophiles, 0 to 20 degrees Celsius. Cycrotrophs, 0 to 35 degrees Celsius. Mesophiles, 20 to 45 degrees Celsius. Thermophiles, 55 to 85 degrees Celsius. The last one, hyperthermophiles, which can go up to 113 degrees Celsius. Okay, this is the temperature. Next one is water activity. This one is very tricky concept. What is water activity? Lots of the time, if you ask a question, they will say, water amount of a food products. That is wrong. Because that is called moisture content. Unfortunately, these two are not equal. What is the moisture content? If I have a food products, okay, I'm going to split them. There is a wet area, there is a dry area. Is that right? There is two methods to calculate the moisture content. It could be the wet area divided by the dry area, or the wet area divided by the wet and the whole dry area. These two possibilities, we call it dry wet and solid wet and the wet wet. That's the moisture content. Here we talk about water activity is a different situation. Here we're going to talk about is vapor pressure. What is that? You need to know a little bit of physics. Okay, above I have a utensil like this. Below I have a utensil like that. Let's talk about something. Here I'm going to put water. Okay, I put water there. H2O is a water molecule. In this utensil, the water is there. Water molecule is moving. Some of the water molecules are going to go up. Some of them go down. They're going to do a balance. So there's a pressure right above the water line. This is called vapor pressure. And you know that if the vapor pressure equals atmosphere pressure, what's going to happen? Can you tell me in 5 seconds what's going to happen? The vapor pressure equals atmosphere pressure, what will happen? Yeah, boiling will happen. Very good. The boiling will happen. Of course, assumption there's a heat here, okay? Now, let's say we have a food products. I have a ham here. Okay, a ham is right here. The ham has a salt, is that right? The ham has a sugar, has a fat. Then the water molecule also there. Okay, we have a water molecule. So the water molecule will go out. Some will go down. Because you have a salt, you have a sugar, you have a fat. So the water molecule are not going to be completely go out. Lots of them, they will be dragged down. They will be dragged down. Or maybe keep contracted there. So therefore the vapor pressure here will be less than the vapor pressure of a pure water. So So in the scientific area, we give a pure water vapor pressure is 1.000, and the above one is less than that. So somehow like 0.8 could be 0.9, and there's a ratio between that. This ratio comes out with water activity. Acronym is AW. This is called water activity. So once I describe this to you, what really we talk about water activity is available water can be used by bacteria. In the food microbiology or food chemistry area, we call it available water to do chemical reaction. Here we talk about is available water for bacteria growth. And I want to tell you one thing. The moisture content and the water activity, they usually looks like this. Sometimes looks like that. Not linear, but they have a correlation. And food products put in the environment, their water will be absorbed and dissolved. They reach a balance we call it equilibrium water moisture amount. This is come out with a terminology we call relative humidity. And the relative humidity is equals 100 multiplied by water activity. Okay? So just want to let you know that is what water activity means. Water activity you can test in the lab. Hot dog, for example. Water activity is very high. 0.995. Beef jerky is dry. You know that it's dry, 0.7 maybe, 0.8. How about summer sausage? How about salami? Those are fermented products. Those kind of like 0.9. So these are still the bacteria can grow there. Based on the water activity, the bacteria could be categorized into the different categories. Very simple is halophiles. If they grow optimal, more than 0.2 more of the salt concentration, we call it halophiles. If they can grow more than 2 more, we call it extreme halophiles. Where we can find these halophiles? Great Salt Lake in Salt Lake City, Utah. You will see it. You can taste some of the lake very salt. The bacteria survived there, can survive in a very, really low water activity environments. That's we call it extreme halophiles. Okay, so we're going to end up here today, and then we keep talking about oxygen requirements when we come back from the holidays.